less than 4/100ths of an inch thick. Yet it is the starting point for thousands of microchips, carrying the power that drives the entire global technology industry. To create a silicon wafer like this, everything begins with quartz rock extracted from deep beneath the Earth's surface. After more than 2 months of purification, the silicon is pulled into a single crystal ingot, sliced into thousands of ultra-thin wafers, and polished with nanometer-level precision. Only then does it meet the exacting standards required to become the foundation of the semiconductor industry. So how can quartz buried deep underground be transformed into the foundation of the entire digital age? Join Factron Process as we uncover the complete silicon wafer manufacturing process right now. The semiconductor industry is racing at the nanometer scale, yet few people realize that most modern silicon wafers are still produced using a principle developed more than a century ago. That journey began in 1916 when scientist Jan Tralski invented the crystal pulling method. Remarkably, more than 100 years later, this same principle remains the foundation for producing the majority of silicon wafers worldwide, making it one of the most enduring and influential technologies in the history of the semiconductor industry. From a laboratory invention, silicon wafers have grown into a multi-billion-dollar industry. In 2025 alone, the semiconductor wafer market generated approximately $11.4 billion in revenue, with total wafer shipments reaching nearly 13 billion square inches. These figures not only reveal the enormous scale of the industry, but also show that every silicon wafer is an indispensable link in the chain before any modern microchip can be created. If semiconductor chips are the brains of electronic devices, then silicon wafers are the foundation on which those brains are built. A wafer is not a chip. Instead, it serves as a platform where engineers can construct hundreds or even thousands of chips simultaneously across a single surface. In simple terms, a silicon wafer is a thin, circular disk made from silicon of extremely high purity. Every circuit, transistor, and microscopic component within a chip is fabricated directly onto the surface of this wafer. What sets a silicon wafer apart from most other materials is that the entire disk is formed from a single continuous crystal, rather than being assembled from countless smaller crystals. This allows the wafer's entire surface to maintain an almost perfectly uniform structure and quality, enabling it to meet the extraordinarily strict requirements of modern chip manufacturing. It may be hard to believe, but the journey behind the world's most advanced microchips begins with nothing more than raw quartz rock buried deep beneath the Earth's surface. Silicon does not naturally exist in a pure form. Instead, it is bonded with oxygen as silicon dioxide, which can make up as much as 99% of quartz ore. Mining begins when hydraulic drilling rigs bore hundreds of holes, each reaching about 60 feet into the rock face. Once the holes are loaded with explosives, the entire area is evacuated and the charges are detonated simultaneously. In just a few seconds, more than 20,000 tons of rock are shattered, releasing quartz deposits that have remained underground for millions of years. The quartz ore is then loaded onto massive haul trucks and transported to the processing plant. There, the large rocks pass through several stages of crushing before being screened by size and thoroughly washed to remove soil, dust, and any material that fails to meet the required standards. The result is uniformly sized quartz, ready to be fed into the smelting furnace. To separate the silicon from oxygen, the quartz ore is mixed with coke and fed into an electric arc furnace. Inside, an extremely powerful electrical current generates temperatures exceeding 3,600 degrees Fahrenheit, hot enough to break the bonds between silicon and oxygen. At this temperature, the oxygen reacts with carbon to form carbon monoxide gas, while the molten silicon flows to the bottom of the furnace, where it is collected separately. After being tapped from the furnace and allowed to cool, the silicon solidifies into silvery gray chunks with a purity of up to 98%. This is known as metallurgical grade silicon, a material widely used in metallurgy and alloy production. But for the semiconductor industry, even this level of purity is still nowhere near enough. At this level of purity, the greatest threat comes from contaminants so small that they are invisible to the naked eye. Before the silicon enters the advanced refining process, the process gases, pipelines, equipment, and every contact surface must be strictly controlled. In sensitive processing areas, workers wear dust-resistant and anti-static protective clothing to prevent any foreign material from entering. Even the slightest trace of contamination can compromise the quality of an entire batch of silicon. The metallurgical-grade silicon produced in the previous stage is still not pure enough for chip manufacturing, so it must undergo chemical refining. First, the silicon is converted into a gaseous compound, making its impurities easier to separate. After several purification cycles, the compound is fed into a CVD reactor, a system based on chemical vapor deposition. Inside the reactor, at temperatures of around 2000 degrees Fahrenheit, pure silicon separates from the gas and deposits layer by layer onto silicon rods. This process continues uninterrupted for several days, gradually increasing the size of the rods. Once complete, they can weigh several hundred pounds and reach a purity of approximately 99.999999%, making them among the purest materials ever produced by humankind. After chemical refining, the polysilicon rods are broken into smaller chunks and loaded into the quartz crucible of a Czochralski crystal pulling furnace. Inside, the heating system raises the temperature to approximately 2507 degrees, transforming the silicon into a glowing pool of molten material. A minute amount of boron or phosphorus may also be added to control its electrical properties. Once the temperature and flow have stabilized, a seed crystal is lowered until it gently touches the surface of the molten silicon. The seed rotates as it is pulled upward at an extremely slow rate, while the crucible turns in the opposite direction to distribute the heat evenly. The machine continuously adjusts the pulling speed, first forming a narrow neck to minimize defects, then widening the shoulder before maintaining the cylindrical body at the required diameter. At the point of contact, the molten silicon solidifies and replicates the seed crystal's atomic structure. Over many hours, layer after layer builds into a single crystal silicon ingot nearly 7 feet long and weighing more than 220 pounds, the foundation from which thousands of ultra-precise wafers can be sliced. Once fully cooled, the single crystal silicon ingot enters the machining area. Its two ends are removed first, since these sections may contain less uniform crystal structures. The cylindrical surface is then ground smooth and brought to the standard diameter, typically 12 inches. A small notch is cut into the ingot, allowing automated equipment to identify its crystal orientation throughout the stages that follow. The finished ingot is then loaded into a diamond wire saw. Hundreds of ultra-thin, diamond-coated wires move at high speed, slicing through the crystal-hard silicon with extreme precision. This method reduces cracking and minimizes the valuable material lost as cutting dust. Depending on the ingot's length and the required thickness, a single ingot can produce several hundred to more than 1,000 wafers in one slicing cycle. After cutting, the wafers are thoroughly cleaned to remove silicon residue. Automated systems inspect their thickness and warpage, while the sharp edges are carefully rounded to prevent cracking before the wafers move on to polishing and chip manufacturing. Even when sliced with an extremely precise diamond wire saw, every wafer is still left with millions of microscopic scratches. That is why its surface must be finished to near perfection. First, the wafer is immersed in a mixture of nitric acid, hydrofluoric acid, and acetic acid. This chemical bath gently dissolves the layer of silicon damaged during slicing without affecting the flawless crystal structure beneath it. Next, the wafer enters a polishing machine. Inside, a continuously rotating polishing pad works together with a slurry containing ultra-fine abrasive particles, gradually removing layers of silicon only a few dozen nanometers thick, mere millionths of an inch at a time. The purpose of this stage is not simply to make the wafer shine, but to create a surface that is almost perfectly flat. After polishing, the wafer is rinsed with ultra-pure water thousands of times purer than ordinary drinking water. Nearly free of minerals, metal ions, and dust particles, it washes away every remaining trace of chemicals and abrasive material from the surface. Finally, an optical inspection system scans the entire wafer for microscopic particles, scratches, and defects. A single dust particle measuring just 0.1 micrometer, or about 4 millionths of an inch, is nearly 700 times smaller than the diameter of a human hair, yet it can damage multiple chips on the same wafer. Only wafers that pass every inspection are cleared to move on to the next stage. After passing every quality inspection, the silicon wafers are finally ready to leave the factory. A single silicon wafer can take more than 2 months to complete, yet one speck of dust, or even the slightest impact during transportation, could destroy everything achieved along the way. First, each wafer is classified by diameter, thickness, dopant type, and quality grade. At the same time, a laser identification code is engraved along its edge, allowing manufacturers to trace the complete history of every wafer, from its raw material batch and production date to its quality inspection results. The wafers are then placed inside specialized carriers for 12-inch wafers, known as EVOOPs. Individual slots hold each wafer only by its edges, preventing the polished surfaces from touching one another. The carrier is sealed in a clean environment to protect the wafers from dust, moisture, and physical shock during transportation. Finally, the sealed wafer carriers are packed inside a clean room before being shipped to chip fabrication plants around the world. From this point forward, these nearly flawless silicon wafers will become the foundation for billions of semiconductor components used in smartphones, computers, automobiles, and countless other modern electronic devices. Today, silicon wafers form the foundation of nearly every modern electronic device. According to industry estimates, more than 1.2 billion smartphones, over 250 million personal computers, and tens of millions of servers are produced each year, all relying on components manufactured from silicon wafers. Their role is becoming increasingly important in the automotive industry. A modern car can contain more than 3,000 electronic components, while a high-end electric vehicle may use over 5,000 to control its motors, cameras, radar systems, displays, entertainment features, and advanced driver assistance technologies. Beyond consumer electronics and automobiles, silicon wafers also play a critical role in medical equipment, aerospace, telecommunications, and renewable energy. MRI scanners, satellites, GPS navigation systems, 5G networks, and solar panels all depend on components or sensors developed from silicon wafers. The solar industry alone installed more than 590 gigawatts of new capacity in 2024, with crystalline silicon solar cells accounting for over 95% of the global market. As artificial intelligence, robotics, autonomous vehicles, and data centers continue to expand, demand for silicon wafers will keep rising, reinforcing their position as one of the most important materials in modern industry. A flawless silicon wafer is only the beginning. Its true value is created only after it enters a semiconductor fabrication plant, where its surface undergoes hundreds of manufacturing steps performed with nanometer-level precision to form a complete chip. The process is so complex that it is considered one of humanity's greatest engineering achievements. And that is the journey we will explore in the next part of this video, the semiconductor chip manufacturing process. Manufacturing a modern semiconductor chip can require an investment of more than $20 billion in advanced fabrication facilities and take up to 3 months to complete a single production batch. Throughout that journey, the chip must pass through thousands of processing steps, from printing circuits at the nanometer scale and creating billions of transistors to building multiple layers of microscopic interconnections, testing, and packaging with near absolute precision. Every stage must be executed flawlessly, because even the smallest defect can render an entire chip worthless. In today's video, join Factron Process as we explore the complete semiconductor chip manufacturing process and discover why it is considered one of the greatest engineering achievements of modern industry. Few people realize that semiconductor chips have existed for less than 80 years, yet they have already become the foundation of the entire modern technological world. Since the first transistor was invented in 1947, the semiconductor industry has grown into a market worth more than $600 billion a year, producing trillions of chips that support nearly every aspect of human life. Smartphones, computers, automobiles, and even aircraft, medical equipment, satellites, and enormous data centers could not function without these tiny components. What makes semiconductor manufacturing truly remarkable is that its fabrication plants are cleaner than many hospital operating rooms. Air filtration systems must run continuously to remove airborne contamination because even a microscopic particle landing in the wrong place can damage the chip's incredibly small circuits. These extreme requirements have turned semiconductor manufacturing into one of the most precise production processes ever created by humankind. From the outside, a semiconductor chip appears to be nothing more than a small black square. But beneath that protective shell lies an entire microscopic city, built on one or more silicon dies originating from a wafer only about 0.775 millimeters thick. A chip can contain tens to hundreds of billions of microscopic transistors, acting as tiny electrical switches that turn on and off billions of times every second to perform complex calculations. These transistors are connected through multiple layers of extremely fine conductive interconnects, forming intricate networks that allow electrical signals to travel at extraordinary speeds. After being separated from the wafer, the silicon die is placed inside a protective package and connected to electrical contacts, allowing the finished chip to communicate with a circuit board and operate inside an electronic device. It is this extraordinarily intricate structure, packed into such a tiny space, that has transformed the semiconductor chip into the brain behind most modern technology. Before entering a fabrication plant worth more than $20 billion, every chip exists only as digital data inside a computer. At this stage, engineers determine exactly what the chip will be designed to do. From there, they develop its architecture, memory capacity, internal communication systems, and network of interconnections, while carefully balancing performance, power consumption, and heat generation. Once the architecture has been finalized, specialized semiconductor design software begins arranging every component within an area measuring only a few hundred square millimeters. In today's most advanced processors, the blueprint can contain more than 200 billion transistors, demanding near absolute precision. To ensure that everything works correctly, the design undergoes a long series of simulations and automated verification procedures. Engineers continuously optimize performance, signal integrity, and power consumption until every technical requirement has been satisfied. By the end of this stage, the chip's entire internal structure has been fully defined and is ready to enter production. If the chip design is its brain, the photomask set is the printing template that determines every detail that will eventually appear on the wafer. A modern processor may require more than 100 photomasks, with each mask defining a separate structural layer, such as the transistors, conductive pathways, or the microscopic vias connecting different levels of circuitry. To manufacture these masks, the completed design data is transferred to an electron beam mask writer. A tightly controlled electron beam scans point by point across a quartz plate coated with an electron-sensitive resist, creating patterns corresponding to circuit features only a few nanometers wide on the wafer. Producing just one photomask can take anywhere from 18 hours to more than an entire day. Before any circuit pattern can be created, the silicon wafer must enter an environment approaching absolute cleanliness. A single dust particle, dozens of times smaller than the width of a human hair, can potentially damage thousands of chips on the same wafer and cause losses reaching hundreds of thousands of dollars. From this point forward, every operation takes place inside a clean room where temperature, humidity, and air quality are strictly controlled every second. The wafers are first placed inside sealed containers known as FOUPs, or front-opening unified pods, which isolate them completely from the surrounding environment. From there, the Automated Material Handling System, or AMHS, receives the UPS and transports them through an enclosed network of overhead rails running across the fabrication plant. These containers continuously glide above the production floor, automatically accelerating, slowing down, changing direction, and stopping with exact precision in front of each processing tool under the control of a central computer system, requiring almost no direct human intervention. When a FOUP reaches the correct processing station, a robot carefully removes each wafer and places it inside the machine. The wafer is then washed with ultra-pure water and dried using nitrogen gas to remove dust, impurities, and any remaining chemical residue before entering the production line. Once the wafer has been cleaned to an extraordinary level, it enters the stage that creates the foundation for its microscopic structures, material deposition. During this process, an ultra-thin film of material is deposited evenly across the wafer's surface. Only after this layer has been completed can the wafer move to the photolithography station. To prepare it for patterning, a spin coater spreads a light-sensitive material known as photoresist across the wafer, forming an extremely thin and uniform film. Depending on the size and complexity of each circuit layer, the wafer is then transferred into either a DUV or EUV lithography system. For the smallest and most critical circuit layers, conventional light no longer provides sufficient resolution, so an EUV lithography system worth hundreds of millions of dollars must be used. Inside a vacuum chamber, EUV light, with a wavelength of just 13.5 nanometers, is reflected and focused by a system of ultra-precise mirrors, altering the chemical properties of the photoresist and revealing the first microscopic circuit patterns on the wafer. At the previous stage, the circuit pattern existed only within the coated material. To transform that pattern into a physical structure, the wafer enters a plasma etching system, where high-energy plasma removes selected areas of material and creates microscopic trenches and structures with nanometer-level precision. Building a complete transistor requires repeated cycles of material deposition, photolithography, plasma etching, cleaning, and other material processing techniques. At specific locations where the electrical properties of the silicon must be altered, the wafer undergoes a process known as ion implantation. A particle accelerator fires dopant ions directly into the silicon crystal lattice, after which the wafer is placed inside a high-temperature furnace to repair damage within the crystal structure and activate the electrical properties of the implanted ions. Layer by layer and process by process, tens of billions of transistors gradually take shape inside the chip's silicon core. After billions of transistors have been formed, they still cannot function until they are electrically connected. To create a complete processor, the wafer must pass through another series of highly precise manufacturing stages that form microscopic conductive pathways. First, a layer of insulating material is deposited across the wafer to separate the different circuit levels. Photolithography and etching systems then create millions of microscopic holes and trenches through this insulating layer, forming the roads through which electrical signals will travel across the chip. Metal, primarily copper, is then deposited into these openings, creating a microscopic wiring network that connects the transistors. Any excess metal remaining on the surface is removed through chemical mechanical planarization, or CMP, leaving the wafer flat enough for the next layer to be constructed. This cycle is repeated many times, producing multiple interconnect layers stacked on top of one another and allowing billions of transistors to operate simultaneously at extraordinary speeds. In reality, quality control does not wait until the final stage, but takes place throughout the entire fabrication process. However, before the wafer can be divided into individual chips, it must undergo a final electrical test and surface inspection to ensure that its structures operate as designed. After every critical circuit layer is completed, the wafer passes through automated metrology systems. Ultra-high-resolution scanners continuously inspect the surface for dust, scratches, or abnormal circuit patterns, while other systems measure feature dimensions, material thickness, and the alignment accuracy between different circuit layers. Every defect, even one measuring only a few nanometers, is marked on a wafer map to identify its precise location. Finally, the wafer is transferred into a wafer probe system. Thousands of microscopic probes make contact with test pads on each chip, transmitting electrical signals to determine whether the device functions correctly. The results are compiled into the wafer map, clearly identifying the locations of known good dies and defective ones. Through this rigorous quality control process, only dies that meet the required electrical and quality standards are allowed to continue into packaging and final assembly. After hundreds of fabrication stages, the wafer reaches a decisive boundary. It must be divided into individual chips, known as dies. Depending on the material and structure of the product, the wafer may be diced using a diamond blade, plasma technology, or a laser system. For advanced chips or products that are highly sensitive to contamination, stealth dicing is often preferred. Instead of cutting directly through the wafer's surface, the system focuses a laser beam inside the wafer to create a modified layer along the boundary of each die, minimizing debris and reducing damage to the surface. The adhesive tape holding the wafer is then stretched outward, and the resulting force causes the wafer to fracture along the prepared lines, completely separating the individual dies. Using the defect map generated during the previous inspection stage, robotic arms carefully pick up the known good dies and transfer them to the packaging line. The bare silicon dies are now ready to be mounted onto a substrate and fitted with their protective armor. In many modern packaging processes, flip chip technology is used. The die is turned upside down and connected to the substrate through thousands of microscopic solder bumps. The assembly then passes through a reflow oven, where the solder melts and forms permanent electrical connections, before a specialized epoxy known as underfill is injected into the narrow gap beneath the die to increase the package's mechanical strength and long-term reliability. For advanced AI processors or memory devices that require complex three-dimensional stacking, hybrid bonding becomes the preferred technology. The two dielectric surfaces are thoroughly cleaned, aligned with extreme precision, and bonded directly together. A subsequent thermal process allows the copper contact pads on both surfaces to diffuse into one another, creating strong and reliable electrical connections. Finally, the chip is encapsulated in protective molding and fitted with a heat spreader. Before shipment, the devices must undergo burn-in testing, during which they are operated under elevated temperatures and controlled electrical stress to reveal potential early failures. Their electrical performance and real-world functionality are then tested so they can be sorted into different quality and performance categories through a process known as binning. Each finished chip is marked with an identification code using a laser, placed into a shipping tray, and prepared for delivery. To manufacture a chip no larger than a fingertip, the semiconductor industry must combine hundreds of production stages with precision measured in nanometers. From designing hundreds of billions of transistors and fabricating photomasks, to printing circuit patterns with EUV light, packaging, and final assembly, every step must achieve near absolute accuracy. A single microscopic defect or alignment error can render an entire chip useless. Today, these tiny chips can be found inside nearly every device around us, from smartphones, computers, and automobiles, to satellites, robots, and artificial intelligence systems. They are more than technological products. They have become the foundation on which the modern world operates. Thank you for joining Factron Process on this journey through the complete manufacturing process behind one of the most complex products humanity has ever created. For more stories about technology, engineering, and the massive industrial processes behind the products we use every day, remember to subscribe to the channel so you never miss our next video. We will see you again on the next journey of discovery.